So let me skip all that detail, and actually we were here that the essence of PBD is that there is a decision maker, which is the client obviously, or building owner. He or she can state a desire that a building be able to perform in a certain way, perform, right. That performance can be in terms of anything. It can be protection of life safety, repair cost, downtime, disruption of use, or any other thing. The engineer uses his or her skill to provide a design that will be capable of achieving these objectives. So those performance objectives from a decision maker becomes your design criteria, and then you have to show that this criteria is fulfilled, right. This design can perform in a certain way that the criteria is fulfilled. So this is the essence of performance based design. The performance objective itself is made of two things: a performance level, which means the condition of the building, the maximum acceptable damage which the owner can accept, right, and that should be combined with the ground motion level, right. So there are several levels of earthquake under which you perform analysis, and there is a different expectation from structure under each of these levels. For example, the performance objectives can be like this: that under a low level earthquake, the building should remain completely intact, but under a moderate level earthquake, which should be defined in a probabilistic manner, which I will show next, for a moderate level earthquake, the building can have some minor damage in the non-structural components only, and for a severe earthquake, the allowable damage can be some cracking in shear walls and columns, right. So these three statements will become your performance objectives, and these three statements are, again, each of them is composed of two things: a ground motion level, earthquake level, and the maximum acceptable damage at that level, which is called the performance level, right. So these two things they are combined, and this becomes our performance objectives. So the very first thing in PBD is that you sit with the client and you agree upon on the performance objectives, and actually there is a design criteria document. In conventional design we also have this document, design criteria, and in conventional design this document actually states what loading was used, what building code was used, what material properties, nominal material properties were used. So conventional design have this document also, but when you perform PBD, this document will also state the agreed upon performance objectives, that these much level of earthquake will be considered, and this is the acceptable level of damage at each level, right. This is the performance level at each ground motion level, right. So the design criteria document will explicitly mention these performance objectives, and the final design report in case of PBD will be all focusing on these performance objectives, right, because the conventional design report, it is focusing on the code compliance, right. It shows that engineer follows code, right. Every page of that design report is targeted towards that final objective, and that is code compliance. In this case, all the details, modeling procedures, analysis, everything, whatever you give in the final design report should actually focus on the performance objectives. They should be focused towards the compliance of those performance objectives, right. Now the point where I ended last time was that in performance based design we define the seismic hazard in probabilistic manner, right. Seismic hazard is generally defined by a ground motion parameter, seismic hazard. This word I will use again and again, and I will explain it more in 1 or 2 weeks, but currently the word hazard means the possibility of occurrence of a potentially damaging earthquake, right. The probability of occurrence of a potentially damaging earthquake is the hazard itself, right. So it is described mathematically by few numbers, and the most common number is peak ground acceleration, right. So, the level of seismic hazard is described by ground motion parameters, and there is a whole list of those parameters, but the most common ground motion parameter is peak ground acceleration, PGA value. But nowadays we have a more refined ground motion parameter. PGA is no more used, by the way, as a standard hazard parameter, but there was a big you can say a long duration during which we were using this PGA, right. So, still it gives a very useful information about hazard level. So, for past earthquakes we can actually directly measure what peak ground acceleration was achieved at a particular location, but for future earthquake this number will come from hazard map, right. So, hazard map gives us the expected peak ground acceleration at different locations in next few years, right. So, this peak ground acceleration previously was defined in, or any other number was defined in deterministic manner, which means that if I say that 0.5 g, obviously this will be an acceleration value, peak ground acceleration. So, acceleration can be you can say conveniently described in g units also, right. G unit is a very convenient way to write acceleration. If you can convert it into any units. If you want to convert it into meter per second square, you should multiply by 9.8. This will become your meter per second square. Similarly, in other units, you can just put value of g and it will be converted into those units. In deterministic manner, when I say 0.5 g, I mean that the maximum peak ground acceleration which can be experienced at that particular site is 0.5 g. There is no probabilistic definition when I say in deterministic framework, but nowadays we define hazard in probabilistic framework, and that is the number of ground motion parameter which can be PGA. It should be associated with a percentage of probability of exceedance in some years, right. For example, x% probability of exceedance PE in y years. So, when I define the PGA number for a particular site in probabilistic framework, I would say that the PGA for that particular site is 0.5 g for this much percentage probability of exceedance in these much years, right. And then for the same site, if I change these numbers, probability of exceedance or the number of years, then this PGA will be changed, right. So, let me give you an example. First, try to understand what this definition means itself. When I say that I write again that this is a particular study area and this is your particular site, this star symbol is your site, and I define that 0.5 g is your PGA number with 10% probability of exceedance, 10% PE in 50 years. First, try to understand this whole thing. What I am saying is that 0.5 g is the PGA number for your site, but there is a probability of exceeding that number also in next 50 years. So, there is a 10% chance that in next 50 years, whatever earthquake will occur, it will produce a PGA greater than 0.5 g, and 90% is the chance that the PGA will be lower than this number, right, in next 50 years. Now, if I change, let us say for 100 years, the number for that same site will be different, right. Actually, this number 50 years is the exposure period. It is generally used as the design life of the building. So, we are interested in this number, but generally this 50 years is fixed and we change this probability, right. So, this whole thing x% probability of exceedance in y years, this whole thing can be converted into another number which is called return period, right. So, I will explain that in the seismic hazard lecture again, but currently just try to understand what is the meaning of this whole thing. When I say this number PGA at this much probability of exceedance in this much years. So, at least you should know what I mean actually from that whole phrase, right. So, 50 years is generally considered as a standard exposure period, and whenever we used to report a probability of exceedance, we report it for 50 years, next 50 years. So, I can say 2% probability of exceedance in 50 years, 1% probability of exceedance in 50 years, 10% for example. So, 0.5 G at 10% probability of exceedance in 50 years means that if you consider next 50 years to be the design life of your building, then you should expect that there will be 10% chance that your actual PGA from future earthquake will be more than 0.5 G. But there is a 90% chance that the actual PGA in next 50 years will remain below 0.5 G. So, you can think of this 10% as an acceptable risk, right. And if I say that for the same site, this star, tell me the number for PGA number for 2% probability of exceedance in 50 years. Now, I reduced the probability of exceedance from 10 to 2%. Will the number for the same site will remain same, or will go up, or will go down? It will go up, because now I am saying that the number of PGA will have a 98% chance that the future 50 years PGA will be lower than this, right. And there is only 2% chance that the future PGA will be more than this. So, obviously, the number corresponding to this 2% probability of exceedance in 50 years will be higher for the same site, right. So, it can be like 0.8 G, right. So, now as a designer you have choice in PBD. You design your building for 0.5 G on a lower loading and make your structure economical, right. But then you will have 10% probability associated with your structure that it may experience a PGA more than its design PGA. And also there is an option for designing your structure on 0.8 G, right. Your structure will become costly, client will resist, but then at the same time you have only 2% chance that the next PGA will be more than 0.8 G, next 50 year PGA, right. So, these three are few examples actually of three different levels of future earthquake, because if I say that for 10% probability of exceedance for the same site, the number will be 0.5 G. For 2% probability of exceedance in 50 years, the number will be, let us say, 0.8 G. If I say 1% probability of exceedance, it will be even higher than 0.8 G, right. So, which means that maybe it is 0.9 G maybe, right. So, which means that as the probability of exceedance reduce, the PGA for that particular same site increase, right. So, actually there is a relationship between them. If I plot probability of exceedance in 50 years on y axis and design PGA for the same site on x axis, I will get a line like this, which is actually reducing. So, now as a designer I have a choice that I design on 0.5 PGA, 0.5 G PGA with a higher probability of exceedance, or I design on a higher PGA, maybe 0.8 G with a lower probability of exceedance, right. So, these three examples at the bottom which I am encircling now, they are three different ground motion levels, three different earthquake levels, right. So, now which level should be used for design? Next question is this one. Actually, different guidelines of performance based design guide us about what levels of ground motions should be used for PBD for different kinds of structures. For example, for buildings, there are 3 different ground motion levels which you run the analysis for, right? These 3 are exactly the same 3 which are shown here as an example. 2% probability of exceedance in 50 years, 10% probability of exceedance in 50 years, and 50% probability of exceedance in 30 years. These 3 definitions of seismic hazard, probabilistic definitions, are considered a standard for the design of buildings, right? For the performance based evaluation of buildings. This one, 10% probability of exceedance in 50 years, this middle one is called the design basis earthquake for buildings, right? Design basis earthquake, DBE. I will go into more detail in next slides. Today is only the introductory class. So this middle one is called DBE level, design basis earthquake. As the name indicates, that this is the level which is generally used for the design of building, right? This 2% probability of exceedance, which is a higher level earthquake, right? It is called maximum considered earthquake, MCE level, MCE, maximum considered earthquake. This is a higher level compared to design level. And this one, the bottom one, is called the service level earthquake. It is the lowest level, service level earthquake, right? SLE, service level earthquake. Now these 3 standard definitions are used for PBD of buildings, but for bridges these definitions are different. For dams these definitions are different, right? For example, dams, I know that they can be designed for 0.5% probability of exceedance in 50 years. This is an example of seismic hazard definition used for the design of dams. 0.5% chance that your number in next 50 years will be higher than this number, whatever is the number at this definition, right? So the summary is that in probabilistic framework, the seismic hazard is defined not only as one fixed number, but that number is added or coupled with the probability of exceedance in 50 years or in some years, right? So if I go back and show you the same hazard map of Pakistan, this hazard map is actually following that probabilistic definition, and it is all the PGA numbers are not deterministic, which are shown here with colors. These numbers are actually following this 10% probability of exceedance in 50 years, right? So which means that if I pick the PGA value from this particular location, it may be, let's say, 0.25 G. Now this 0.25 G is following this definition, 10% probability of exceedance in 50 years. So whenever you make a map, hazard map, you follow a particular definition, and at that definition you report PGA values or any other hazard values, right? So each number on this map has a 10% chance that in next 50 years the actual PGA is more than that number, right? So if you design for 0.25 G following a particular hazard map which is having this definition on top, there is a 10% chance that you may experience in next 50 years a higher number, right? But that 10% is in kind of an acceptable chance, right? You may design for 2% probability of exceedance also, but correspondingly the PGA number will be far higher than that, and your design will be costly. Now as a PBD engineer, some developer can come and it says that I don't want to follow the intention of building code, I want to remain completely elastic, intact, even at a very rare earthquake, right? For example, 2% probability of exceedance in 50 years, 2%, very rare earthquake. So what you will do simply, you will use a number of PGA as a design PGA corresponding to 2% probability of exceedance in 50 years, right? So one of the output from the PSHA process is a hazard map for each site, a map containing probability of exceedance in y-axis and the PGA number on x-axis, right. So, at each dot on this map, I have this curve which will look like this. As you reduce the probability of exceedance, the PGA for the same site will increase. Now, the map is constructed by following one definition, one map, one definition, right. For example, this is 10%, this is 2%. So, what I can do is that for each dot or each pixel in this map, I can construct the hazard curve from PSHA process and then fix one definition, like let us say 10%, and pick the PGA value from each of these curves for all these pixels and convert that into a map. Now, that map will show PGA values at a fixed definition of hazard, and that will be 10% probability of exceedance in 50 years. Now, you can also make a different map for 2% probability of exceedance, that will show higher values compared to these numbers, right. So, you will use a higher number to satisfy that requirement that even for a rare earthquake, the building should remain elastic or building should have a minor damage. So, in PBD, the hazard is not fixed. The summary of whole discussion, although I will continue that discussion in next session also, but the summary is what? That hazard number, PGA number for a particular site is not fixed. It is always coupled with a probability of exceedance in some years, right. So, this is one of the key features of performance based design, that you do not analyze the building for one fixed hazard level, you analyze it for 3 levels at least, right, or 2 levels maybe, one lower than the design level, one higher than the design level. And there are standard specifications and guidelines of PBD which guide us that what probability of exceedance we should use for different purpose. For example, as I have explained that this 10% probability of exceedance in 50 years, it is a standard definition at which the buildings should be designed, right. So, the conventional building codes also, when they report the hazard map, they report on this probability of exceedance. But in PBD, what you further do is that you also analyze the building for 2% probability of exceedance, higher level, and then see what damage your design is going to have, right, whether the intention of the building code or the intention set by a particular building owner is satisfied or not. And then you also analyzed for a lower level than design level, which is called service level earthquake, having a 50% probability of exceedance in 50 years. Now, just think what it means, 50% chance that in next 30 years the PGA will be exceeded by this number. So, it is a frequent earthquake, it is an earthquake which is not that rare, which will at least come once or twice in the design life of the building. It is a frequent earthquake. So, the PGA number will be lower, because for frequent earthquakes PGA will be lower, for rare earthquakes PGA will be higher. So, you will analyze your building not only for DBE level, but for MCE and SLE level also. And for MCE level, since it is a higher level than design, then it means that your building is going to get damaged. And if you are expecting a damage, then the structural model used for this analysis should be capable enough to simulate cracking and yielding and that damage. It cannot be that you use an elastic model and apply a very high level earthquake, because that analysis will be completely wrong. If you are expecting a damage, then the structural model should be non-linear then, right. So, therefore, for design level and for service level evaluation, you can use a linear elastic model, conventional model, but for MCE level analysis, you have to make a non-linear model and do non-linear analysis and modeling everything. Yes, obviously you can make a hazard map at any definition of hazard. Generally, the reported hazard maps are at 10% probability of exceedance, but you can also make hazard map at 2% probability of exceedance, the numbers will be higher. You can make a hazard map at 50% probability of exceedance in certain years. The numbers will be lower than that, right? So in the new building code of Pakistan, you will see hazard maps at different probabilities. DBE level, MCE level, SLE level, some intermediate level also, because for bridges generally the design hazard level is somewhere between DBE and MCE for buildings. It is 1000 years return period, which is somewhere between DBE and MCE for buildings. So this number, X% probability of exceedance in Y years, this number, as I have explained earlier, that this can be converted into another number which is called return period. I will explain that in next class, but the same information like 2% PE in 50 years can be also described by another number which is return period, right? So each of this MCE, DBE and SLE level have a return period, right? So either you report return period or you report probability of exceedance in certain years, it's the same thing. How to convert between them, I'll explain in PSHA class. So again the summary is, I have to conclude everything before we finish this class today. Performance objective is a combination of two things: hazard definition and the resulting damage which can be acceptable by the client. So for DBE level, he can say I can expect this damage. For MCE level, maybe some damage can be allowed, and for SLE level, no damage is allowed. So these kind of performance objectives you may expect from clients in PBD. Now the performance level, which is this one, also has some standard templates. Just like the ground motion level have some standard definitions which can be used in context of buildings, bridges, dams, anything. Similarly, performance levels also have some templates, right? So these templates we give names also in performance based design guidelines. These templates are given names also. For example, there is a standard performance level called operational, which means complete intact, no damage whatsoever, operational. Immediate occupancy means very minor damage. People can go out during an earthquake, but then come back and then start doing the same thing. The building can be immediately occupied after an earthquake. This is immediate occupancy or IO level. IO level. Life safety means that there can be moderate damage, but there should be no loss of life, right? So the level is moderate. It can be repaired, right? And collapse prevention means that there can be significant damage, but the structure should at least remain standing. Collapse should be prevented. CP, collapse prevention, right? So these four are templates of performance, right? So client can simply say that I want IO level for this much level. For example, he can say that for SLE earthquake, I want operational. For DBE, I want life safety. For MCE, which means 2% probability of exceedance in 50 years, I want CP. Or then you can think of any combinations client can set for you, right? But these are some standard templates, right? So you can directly show or explain what LS means. Now LS can be explained to any client, or IO can be explained to any client, right? So that information sharing will be there in case of PBD. So there is a descriptive definition of what operational level mean or what immediate occupancy mean, right? So immediate occupancy mean that there can be very small minor structural damage, maybe few minor cracks which are not structural, and losses can be less than 15%, maybe electricity system can get damaged, but no structural loss. IO means this. Then CP can have some damage. There are very good depictions of what IO, LS and CP mean in different performance based guidelines. I will share few of them with you. and give you links for download also at the end of this lecture. For life safety, losses can be less than 30%. Building may not be safe for reoccupancy. There is some repair which may be required, right? CP means that significant damage is allowed. Structure is almost near collapse, but it is not collapsed completely. So it will still remain standing, so that anyone want to escape can escape, right? So this can be CP level. So these are the templates of damage or performance which you can tell to client and he or she can select, right? These are standard templates. So the very first generation of performance based design guidelines, they were recommending nonlinear static procedures, which are also called as pushover analysis procedures, because the nonlinear dynamic analysis was not that common in late 90s, right? So the first generation of guidelines which are shown here, ATC 40, then FEMA 356, NEHRP guidelines, this is FEMA 356. These are all available, by the way, I'll show you. But they were mostly recommending nonlinear static procedures. But now the next generation of PBD, current state of the art guidelines, they recommend the nonlinear dynamic analysis, nonlinear time history analysis. So you are already familiar with time history analysis, direct integration or modal RHA, but for nonlinear it will be only direct integration. So the computer model used for that analysis will be nonlinear, will be able to simulate all the damages, right? So once the structural performance is established at the result of analysis, nonlinear analysis, you can convert that performance into any other loss. For example, immediate occupancy can be converted into repair cost, it can be converted into downtime, and there are models available which can convert the analysis results into number of casualties also. If you give all that sophisticated information in the model, how much people are there, what is the type of building, and the everything, all that detail, right? So you can convert the performance levels after the analysis into any damage or any loss, casualties, downtime for rehabilitation or repair cost. Obviously for IO everything is 0, and for CP everything will be maximum. Repair cost will be maximum, or obviously for CP maybe repair is not feasible, right? So the bottom line is that all the losses or consequences of non-performance can be quantified. Just remember that Hammurabi's code, where it says that if you do not construct properly, someone is killed, you should be killed in that place, right? So exactly same thing, the consequence of non-performance can be established directly. This much repair cost you have to sustain. Now your choice, you design on a higher number, pay more, or get ready for a higher repair cost in case of an earthquake, right? So everything is in your hand now. So you settle with client what he exactly requires, what is acceptable for him, and finalize a design based on that, right? So as I have said that this methodology is primarily developed for seismic loads, but actually it can be applied to any load. I mean, the philosophy will remain same, that the design criteria shouldn't be code compliance, it should be something related to the performance of the building under that loading. So you will find a pre-standard about the performance based design for wind also, right? So there are performance levels for wind also. They are different than IOLS and CP. These IOLS and CP are for seismic analysis, right? So for wind there will be different performance levels, there will be different definitions of wind hazard, like this much return period thunderstorm, this much return period thunderstorm or wind loading, right? So the philosophy will remain same, but the loading and all that will be different. So if you classify the seismic design approaches, actually we are currently discussing this PBD approach, and as I have said, my whole discussion was about this, that it is superior conceptually from the conventional code based design approach, which is again superior compared to the intuitive design. We actually started this whole profession from intuition, right? But at least when we have developed well researched building codes, the resulting design is better than the intuitive design. But performance based design philosophy is one step beyond those code based design, right? It gives you that freedom, flexibility to try new procedures and go beyond the codal requirements. But there are some other seismic design approaches also, or structural design approaches also, which are mostly coming from interdisciplinary areas and affecting the structural design ideas and philosophies. For example, one is consequence and risk based design, and other is the resilience based design. In these fancy philosophies, we actually think of the structural design as one component of an overall procedure. So we take a holistic overview of the whole procedure. So one building is not just one building, it is an addition to a community, and it will affect environment also, it will affect the skyline of the city, it will be part of the overall big environment or infrastructural, you can say, landscape, right? So when you think of that building as one component of whole overview, then you also entertain the risks associated with the decision of structural design. Any design decision, if it start getting affected by the consequences or associated risk, then it becomes risk based design or consequence based design. So you do not focus only on the performance of that building only, but you also consider the nearby buildings, the overall community, the social aspects, the environmental aspects. When you consider all that and they start affecting your design decision making, then this becomes consequence based design or risk based design. Currently I am also not very clear, and this is still being developed actually, this area, that how this can be converted into several standards and guidelines so that it become an option for conventional structural engineers also. So these approaches will not be in the scope of this course. We will be focusing here only on the performance based design, right, where the actual output is performance. Performance of a building is what matters, right? There is a classification of seismic design procedures based on this idea also: force based design and displacement based design. Now what you conventionally do is, in the code based design is force based design, right? In the code based design, what you do is that you calculate the forces which the future earthquake is going to apply to your structure, right, and then apply to your computer model, and then design the cross section and steel for that loading. So your overall design is based on seismic forces, right? That's why it is called force based design, and those forces are applied and the resulting displacements are checked at the end, right? So displacements they do not have an active role in design, they do not govern design mostly, they are just checked that they should be lower than allowable values. So this is force based design. In the displacement based design, you start with a design displacement. You do not start with a design force calculation, but you start with a design displacement, that this much displacement is allowed in my structure, and you convert that allowable displacement back into allowable force, right, and then check whether the structure can sustain that displacement or not. The cross sections are designed such that the steel is designed such that that design displacement can be achieved, right? So displacement becomes the main design parameter. This is in a nutshell the overall philosophy of all displacement based design procedures, that they start with a selection of a design displacement, right?